Hello everyone, welcome to my YouTube channel. Today we are going to explore the core theories and concepts that make wireless communication possible. We will cover everything from data is converted into signals to how multiple users share the airwaves and finally how modern wireless LAN operates. Before we can understand wireless communication, we need a blueprint of how networks operate. The standard blueprint is the Open System Interconnection or OSI model. The OSI model is comprised of 7 ordered layers: physical, data link, network, transport, session and presentation, and application. Each layer defines a specific part of moving information across the network. However, the dominant communication architecture we actually use on the internet is the TCP/IP model. It is a hierarchical 5-layer protocol suite consisting of the physical, data link, network, transport, application layers. For wireless communication, our primary focus is on the bottom 2 layers. The physical layer coordinates the functions required to carry a bit stream over physical medium, defining the data rates and synchronization of bits. The data link layer takes that physical layer and transforms into reliable link, handling farming, physical addressing, and media access control in wireless networks. These 2 layers face the biggest challenges because the medium is the open air. To send information through the air, we must first understand the difference between data and signals. The data refers to information like text, numbers, audio or video that is usable to person or application. However, data cannot be transmitted directly over network. To be transmitted, data must be transformed into electromagnetic signals. Both data and the signals that represent them can be either analog or digital. Analog refers to information that is continuous, while digital refers to information that has discrete states such as ones or zeros. When we transmit wireless signals, we rely heavily on periodic analog signals. The most fundamental form of this is sine waves or sinusoidal signals. A sine wave is fully described by these characteristics. First, peak amplitude, the absolute value of its highest intensity, which is proportional to the energy it carries. Second, frequency, the number of cycles the signal completes in 1 second, measured in hertz. Third phase, the position of the waveform relative to the time zero. By alternating these 3 characteristics of sine waves, we can embed our digital data into an analog signal that can travel through the air. This brings us to the concept of modulation. Modulation is the process of changing digital signal into bandpass analog signals for transmission. This is circular for wireless communication because we need to transmit our data over specific government-assigned radio frequencies. To share the airwaves without interfering with one another, we do this by taking base carrier signals and modifying its characteristics based on the digital data we want to send. There are 4 primary mechanisms for this. First, ASK or amplitude shift keying. Here, the amplitude of the carrier signal is verified to represent ones and zeros, where the frequency and phase remaining constant. Second, FSK or frequency shift keying. The frequency of the carrier signal is varied to represent data, while the peak amplitude and phase remaining constant. Third, PSK or phase shift keying. The phase of the carrier signals is varied to represent different signal elements. Both peak and amplitude and frequency remain constant. Fourth, QA, quadrant amplitude modulation. This is a highly efficient combination of ASK and PSK. It alters both amplitude and the pace similar sensory to the represent multiple bits per single element, making it dominant method for high-speed digital to analog modulation in use today. Now, what happens when multiple signals need to use the same wirelessly? We use a technique called multiplexing, which allows the simultaneously transmission of multiple signals across the single data link. There are three key ways to multiplex data. First, FDM or frequency division multiplexing. This is an analog technique where signals from different sources modulate different carrier frequencies. These frequencies are combined into a single composite signal. To prevent the signals from overlapping, they are separated by strips of unused bandwidth called guard bands. Second is TDM or time division multiplexing. TDM is a digital technique where multiple connections share the high bandwidth of link by sharing time. Each connection occupies a specific portion of time called time slot, sequentially interleaving the data. Finally, we have OFDM or orthogonal frequency division multiplexing. This is heavily used in modern wireless LANs. It is similar to FDM but with a major difference: all the subbands are used by single source at given time. Because the frequencies are orthogonal, they do not interfere with each other, making it incredibly efficient for the wireless transmission. Multiplexing organizes how data is packed onto a link, but multiple access dictates how stations actually compare for the share that available bandwidth. When we take multiplexing theories and apply them to multiple users accessing a channel, it's called channelization. First, FDMA or frequency division multiple access. The available bandwidth is divided into frequency bands, and each band is reserved for a special station to send its data. Second, TDMA or time division multiple access. Here, their stations share the bandwidth of the signal channel in time. Each station is allocated a specific time slot during which it's permitted to transmit its data. Synchronization is critical here so that the station know exactly when their slot begins. Third, OFDMA or orthogonal frequency division multiple access building. Building on OFDMA assigns different subsets of orthogonal subscriptions to individual users. This allows simultaneous low data rate transmission from several users at exactly the same time. Importantly, OFDMA is the fundamental technology in modern cellular network and Wi-Fi 6, also known as IEEE 802.11ax, making it one of the most relevant technology in wireless communications today. In wireless communication, devices usually need to both send and receive data. This requires duplexing. TDD or time division duplexing is a method of half-duplex communication where devices send and receive data at different times. For example, in TDD systems, a primary device might transmit in even-numbered time slots, while a secondary device transmits in the odd-number time slots. They share same frequency but take turns in time. FDD or frequency division duplexing operates differently. In FDD, transmission and reception occur simultaneously but use two completely separate frequency bands. One band is dedicated to sending data and other one is dedicated to receiving data. This is allowed through fully duplex communication and historically very common in cellular networks. Of course, none of this wireless transmission is possible without the physical hardware, antennas. Antennas broadcast unguided electromagnetic signals through the air. Antennas generally fall into two categories based on how they radiate signal. First, omnidirectional antennas. These antennas send out signals in all directions simultaneously. They are typically used for radio waves and are ideal for multicasting application where there is one sender but many receivers such as AM, FM radio, television and standard Wi-Fi routers. Second, unidirectional antennas. These antennas send out signals in one high force direction because the waves are normally focused. The sending and receiving antennas must be carefully aligned. Examples include parabolic dish antennas and horn antennas, which are used for microwaves. They are highly efficient for point-to-point communication. To bring all these theories together, let's look at real-world application. The IEEE 802.11 wireless LAN, commonly known as Wi-Fi. The architecture is built on Basic Service Set or BSS, which consists of stationaries or mobile wireless stations and optional center-based stations known as the access point or AP. Because a wireless LAN shares the airwaves, collision detection is incredibly difficult. Stations cannot listen and transmit at the same time efficiently. Therefore, 802.11 uses a protocol called CSMA-CA, Carrier Sensor Multiple Access with Collision Avoidance. In this protocol, a station must sense the medium before transmitting. If the channel is ideal, it does not send immediately. It waits for the short period called the interference space or IFS to ensure the channel is truly clear. It also uses a connection window to back off a random amount of time to further avoid collisions. To solve the hidden station problem, where two stations cannot hear each other but try to talk to same access point at same time, the protocol uses control frame called RTS or request to send and CTS or clear to send. These handshake frames act as a reservation system, alerting all other stations to stay silent while the data is transmitted. Finally, once the channel is secure, the data is sent in a specific MAC frame format, which include frame control flags, duration values, 4 separate address fields to handle complex wireless routing, sequence control, the frame body, and FCS for error detections. And that brings us to the end of the video. From converting data into analog sinusoidal signals to modulating it using QAM, sharing the airwaves with OFDMA and TDMA, and avoiding collisions using CSMA-CA. These are the fundamental theories that enable the wireless network we rely on every day. Thank you for listening.